Hi, my name is Andras Krasovets, and today I will present our work on continuous authentication using environmental IoT data. First, let me tell you a short story. Dr. Alice is a surgeon at a local hospital. Her everyday work is unpredictable, therefore she catches on administrative affairs whenever she has time. One day, she is called to an emergency surgery and she forgets to lock her computer before rushing to help. This presents a perfect opportunity for a malicious user to strike, since Dr. Alice's computer session is still active and does not require any form of authentication to continue to work normally. Any skilled malicious user is waiting for such an opportunity, as it allows him to install harmful software to the system, as well as access or alter any sensitive information that Dr. Alice has access to. A hospital scenario is just an example of such an attack. Any public space is susceptible, for example, a hotel lobby, an airport terminal, or a local supermarket, to name a few. To tackle the presented issue, we section our work into three separate parts. With the rapidly expanding IoT sector, we grasped the opportunity to exploit environmental IoT data in order to explore novel methods of authentication. Existing, publicly available datasets predominantly focus on data from mobile devices such as smartphones and wearables. Instead, our focus is on instrumenting the environment so the user becomes an unaware participant in the authentication process. Therefore, our first step is to collect the new environmental IoT dataset and make it publicly available for further research. After the dataset is collected, we explore the potential to use mentioned data as a standalone authentication mechanism and evaluate the informativeness of different sensor modalities we use. Third and final step includes implementing a continuous authentication system that is capable of preventing attacks similar to the one we described in the previous slide. First part of our work revolves around collecting an environmental IoT dataset. As demonstrated in the images, we use different sensor modalities, an accelerometer and a gyroscope attached to the keyboard to recognize users' typing patterns. 4 sensors placed under each corner of a plate, positioned under the mouse and keyboard to recognize the user's stance position. Infrared and Hall sensors strategically placed around the environment to recognize user movement patterns, and PC resources monitoring tool collecting data about the CPU, memory, and network usage, recognizing users' computer usage patterns. We collect data from 21 participants, each performing 3 fairly complex activities. Each of the activities is purposed to simulate an everyday office task. First activity includes copying a body of text from a cardboard card. In the second activity, participants browse the internet in order to find the weather forecast of a place of their choice and suggest some tourist attraction based on it. Last activity requires the user to navigate a series of boxes placed around the environment to find the datasheet that they use to generate a graph using a PC tool they like. Each participant performed each of the activity twice. The collected dataset includes 16 hours of data from 24 different sensors and is publicly available at a given address. With a freshly collected dataset, we ask ourselves a question. Could we use this behavioral biometrics in a similar fashion to how we use passwords or fingerprints, that is, as a one-off authentication mechanism? To answer this, we use the linear discriminant analysis to check for intra-user similarity and inter-user separability. We input data of 1 or 2 sessions of the first activity for 3, 7, and 11 different users into a 2-dimensional LDA and output the results. In every subplot, each color or shape represents a different user, while location of each point is determined by the 2D LDA projection. Separating users based on data of a single session works well. Looking at the example of 3 users, we can see a clear separation. However, introducing even a single additional session limits the user separation capability, as you can observe with the proximity of different colored marks in the bottom row of graphs. Although our users perform the same activity, they tend not to perform it in the same manner every time. Consequently, such an approach is a poor alternative to other one-off authentication mechanisms. Instead, we focused on devising a continuous authentication mechanism that works in conjunction with another one-off authentication method. Relating to the story from the beginning of the presentation, we focused on preventing session takeover attacks. To simulate such an attack, we take the first half of first person's data and make her a legitimate user, and the second half of second person's data and make her the attacker. We combine these halves into a new session and do so for all possible combination of users. Then we train a random forest model using data of all users with the exception of the attacker. We base our decision if there is a session takeover attack taking place by counting the number of trees in a random forest that voted for the most popular user. We call this confidence level. based on which we set a static threshold that is the deciding factor whether an attack has occurred or not. By applying this method, we were able to detect 99% of all session takeover attacks. The lookback values on the graphs represent the number of previous time segments we take into account when calculating new confidence levels. We set ourselves two target scenarios, one emphasizing security and the other emphasizing user convenience. In the security scenario, we were able to recognize the attacker on average after 12 seconds with a false rejection rate, that is, how often a legitimate user is recognized as an attacker at 1%. The user convenience scenario discovered an intrusion on average after 44 seconds while maintaining a false rejection rate at 0.2%. In conclusion, in our work, we collected an environmental IoT dataset and made it publicly available for further research on authentication or any IoT-related topic. We analyzed the applicability of such data as a one-off authentication method and concluded that it cannot match already established mechanisms such as passwords and fingerprints. And finally, we implemented a continuous authentication system based on random forest confidence levels. Our system is able to detect 99% of session takeover attacks while retaining a low user convenience penalty and low detection delay. Our follow-up work based on gathered dataset is a developed method that is able to infer users' identity while simultaneously masking users' current activity and was presented at the 2021 ARES conference in August. That is all from my side. Thank you for your attention.